Tonight, I want to tell you a story about how far humans can actually travel in space and why even the moon may be closer than we think. Imagine you've reached the farthest place any human has ever gone. Standing on the moon, grey dust under your feet. No air, no sound, only silence. Above you hangs Earth, 380,000 kilometers from home, humanity's greatest journey. It feels like you've truly left Earth. If you lined up 30 Earths next to each other, they would exactly fill the gap between Earth and the moon. 30 Earths. That's the distance we proudly call conquering space. Now imagine it this way. Suppose your house is Earth. You step out the door. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps. You stop. That's the moon. 10 steps from home. Sounds close, doesn't it? But those 10 steps are our greatest achievement. In over 50 years since Apollo, we haven't gone farther. No human has stood more than 10 steps from the front door. Now let's keep going. With that same scale, if Earth to Moon is 10 steps, where is Mars? Mars is 2 kilometers away. 2,000 meters. You'd need to walk for about half an hour. And that's when Mars is closest to Earth. When it's farthest, 5 kilometers. An hour and a half walking. We've sent robots to Mars. Those journeys took 7 months. 7 months to travel 2 kilometers on our house scale. You see it now. Space isn't just big. It's big in a way that defies comprehension. But let's go even farther. Pluto, the dwarf planet at the edge of the solar system. On our house scale, 150 kilometers. The distance you'd drive from one city to another. In 2006, NASA launched the New Horizons spacecraft to Pluto. It flew at 58,000 kilometers per hour, the fastest anything has ever left Earth. Fast enough to circle Earth in less than an hour. How long did it take to reach Pluto? 9 years. 9 years of non-stop flying. At 58,000 kilometers per hour. To travel 150 kilometers on our scale. A child born when the spacecraft launched. By the time it reached Pluto, that child was in 3rd grade. Could read, could write, could multiply and divide. 9 years of human life to cross the solar system. And here's the strange part. After those 9 years, New Horizons was still in the solar system. Still hadn't left the yard. Because the solar system doesn't end at Pluto. Beyond it is the Kuiper Belt. Icy bodies tumbling through space. And even farther, the Oort cloud. A swarm of comets surrounding our entire solar system like a giant sphere. How far does the Oort cloud extend? On our house scale, 6,000 kilometers. Flying from Hanoi to America. Across the Pacific Ocean. That's the solar system. That's our yard. Now, let me tell you about Voyager 1. In 1977, before you were born, or when you were very young, humans launched a small spacecraft into space. We called it Voyager 1. On board was a golden record. In the record was music from Earth, the sound of ocean waves, birds singing, human voices saying hello in 55 languages. A message for anyone out there who might find it. Voyager 1 flew past Jupiter, beautiful images of swirling storms bigger than Earth. Then past Saturn, those magnificent rings, made of billions of ice particles. Each one catching sunlight. The photos stunned the world. We saw worlds we'd only dreamed about. Then Voyager kept going, out beyond Neptune, out past the planets, into the darkness, year after year. It flew, decade after decade. The team that launched it grew older. Some retired. Some passed away. New engineers took their places. monitoring signals from a spacecraft that kept getting farther and farther away. In 2012, 35 years after launch, Voyager 1 crossed a boundary. It left the heliosphere, the magnetic bubble our sun creates around its system. It officially entered interstellar space. 35 years, an entire working lifetime from college graduation to retirement, to leave the heliosphere. But here's what's incredible. Even after 35 years, even after crossing into interstellar space, Voyager 1 was still in the solar system, still within the gravitational influence of the sun. And now, it's 2026. Voyager 1 has been flying for 49 years, nearly half a century. It's currently 24 billion kilometers from Earth, so far that signals from it take 22 hours to reach Earth. You send a command in the morning, it arrives the next afternoon. Think about that. 22 hours for a radio signal traveling at light speed, the fastest thing in the universe. And it takes nearly a full day to reach Voyager. Voyager 1 is the farthest human-made object, the fastest, has been flying the longest, a testament to human engineering and ambition, and it still hasn't left the solar system. It's still in the Oort cloud, that vast comet swarm surrounding us. Scientists estimate it will take about 300 more years to completely escape the sun's influence. 300 years. The time from when Isaac Newton discovered gravity to today. The time from medieval kingdoms to smartphones. From sailing ships to spacecraft. All that time, and Voyager will only just be exiting our neighborhood. But suppose Voyager 1 keeps flying. Suppose it continues for thousands more years. Tens of thousands of years, flying at 60,000 kilometers per hour. Never stopping. Never slowing. Where will it go in about 80,000 years? It will pass near another star, AC plus 79,3888. If you care about the designation, it's not a famous star, not a particularly interesting one, just a random star in the cosmic sea. And Voyager will fly past it at a distance of about 2 light-years. Close by cosmic standards. An impossible gulf by human standards. 80,000 years. From the Middle Stone Age to now. From when our ancestors lived in caves, painting on rock walls, hunting with stone-tipped spears, to the age when you hold a computer in your pocket. From the invention of language to the invention of the internet, that entire span of human development would fit inside Voyager's journey to pass near just one other star. And that star isn't even the nearest star to Earth. It's just the one that Voyager's trajectory happens to bring it close to. So what about the actual nearest star? The real next-door neighbor in the cosmic neighborhood Alpha Centauri? Or more precisely, Proxima Centauri, a small red dwarf in the Alpha Centauri system. That's the nearest star to Earth. On a dark night, away from city lights, you can see it twinkling in the southern sky. It looks like all the other stars, just another point of light. But it's not like the others. It's special because it's close. The closest we have. If Voyager 1 flew straight there instead of its current trajectory, how long would it take? 80,000 years. 1,000 human generations. If you traced your family tree back 1,000 generations, you'd reach people who didn't yet have agriculture, who didn't have writing, who didn't have permanent settlements, who were still nomadic hunter-gatherers figuring out how to survive in a wild world. Now trace forward 1,000 generations. What will humans be like then? Will we still exist? Will we still remember Earth? Will we still tell stories about our origins? That's how long it would take. That's the distance to the nearest star. And this is where the story starts to feel crushing. Because all these numbers, these journeys, these timescales, they're based on our current technology. The fastest spacecraft we've ever built. But what if we could go faster? Much faster? What if we could somehow travel at the speed of light itself? The ultimate speed limit of the universe. How long would it take then? 4.5 years. Even at light speed, even traveling as fast as physics allows, even moving at 300,000 kilometers per second, it would still take 4.5 years to reach the nearest star. Light travels from the Sun to Earth in 8 minutes. Just 8 minutes to cross 150 million kilometers. Light could circle Earth 7.5 times in a single second. It's unimaginably fast by human standards. But from Earth to Proxima Centauri, 4.5 years, space is so vast that even light, the fastest thing in existence, takes years to cross the relatively short distance between neighboring stars. And Proxima Centauri is close. It's our nearest neighbor. What about all the other stars you can see in the night sky? What about the thousands of stars visible to the naked eye? The billions visible through telescopes. Most of them are hundreds of light years away. Thousands of light years. Some are on the far side of our galaxy. Tens of thousands of light years distant. At light speed, it would take your entire life to reach them. Multiple lifetimes. Longer than human civilization has existed. And that's traveling at a speed we can't even reach. A speed that physics says is impossible for anything with mass to achieve. So the question becomes, if the nearest star takes 80,000 years to reach with our technology, or 4.5 years even at light speed, what about the rest of the galaxy? What about the rest of the universe? How trapped are we really? Destination 2. The distance to the nearest star, 1000 to 2000, Alpha Centauri, the nearest star to Earth. On a clear night, you can look up and see it sparkling among thousands of other points of light. It looks like all the others, just another star in the infinite scatter of lights across the black canvas of space. But let's try to go there. Not in reality, but in imagination. Let's understand what that journey actually means. Imagine you board Voyager 1. You settle into your seat. If there was one, the engines roar to life. If you could hear them in the vacuum of space, you lift off from Earth, accelerating to 60,000 kilometers per hour. The fastest speed humanity has ever achieved for a spacecraft leaving our planet. Day 1. It's exciting. Earth shrinks behind you. Within hours, it becomes a marble, blue and white and beautiful. The moon passes by in less than a day. You wave at it. First milestone achieved. You're already farther than the Apollo astronauts ever went. Week 1. Mars appears ahead. Still weeks away. You take photos of it growing larger in your window. The sun is still huge in your view. Still bright. Still warming your ship. Space doesn't feel empty. There's always something to see. Planets ahead. The sun behind. You're making progress. Month 1. You finally pass Mars. The red planet drifts by your window. You can see the polar ice caps, the vast canyons, the rust-colored deserts. You think about the rovers down there. Those lonely machines we sent ahead. You're following in their path now. Going farther. The asteroid belt approaches. Small rocks tumble past occasionally. Most of space is empty. But here there's a population of debris, remnants from the solar system's formation. You navigate carefully through this scattered field. Year 1. Jupiter finally arrives. You've been flying for an entire year. 365 days of continuous motion at 60,000 kilometers per hour. And you've reached the giant of our solar system. Jupiter is magnificent, bigger than 1,000 Earths. Those swirling clouds, cream and orange and brown, the great red spot, a storm larger than our entire planet, raging for centuries. You take photos, lots of them. You send them back to Earth. The signal takes an hour now to make the journey. People back home marvel at your images. You're a hero. You've gone so far. But then you look at your navigation display. You check your destination. Proxima Centauri, and you see the distance remaining. You've barely moved on that scale. After an entire year of flight, you've covered such a tiny fraction of the journey that it's almost invisible. It's like taking one step in a marathon that crosses continents. You've started. That's all. Year 10. Saturn is behind you now. Uranus ahead, but still years away. The sun has shrunk. It's no longer a giant disk in your window. Now it's more like a very bright star. Still the brightest object in your sky. But you can look at it without squinting. It's become distant. The messages from Earth take hours to arrive now. You hear voices from home. But they're old. Events from several hours ago. Time enough for lunch. A nap. Dinner. By the time you hear news, it's already ancient history to the people who sent it. You start to feel the isolation. Not physically. The ship is comfortable enough. But psychologically, you're getting farther from everything you've ever known. And the distance is creating a gap in time itself. Communication is becoming difficult. Not impossible, but slow, delayed. Like writing letters to someone on the other side of the world. Except the other side of the solar system. Year 25. Neptune passes by. The farthest planet, pale blue and serene. Beautiful in its remoteness. Beyond it, darkness. Pluto is out there somewhere. But you won't pass close to it. Just more darkness ahead. More empty space. The sun is a bright star now. Nothing more. You can't feel its warmth anymore. The ship relies on nuclear power. The solar panels stopped being useful years ago. Out here, the sun's light is too weak to power anything. Year 50. You're where Voyager 1 actually is now. Half a century of flight. The child who watched you launch is now retired. Their children have children. You've crossed 24 billion kilometers. By any human measure, you've traveled an impossible distance. And yet, on the scale of interstellar distance, you've barely left the driveway. Distance to Proxima Centauri, remaining 99.99%. You've completed 1/100th of 1% of the journey. 1/10,000th. Let that sink in. 50 years of travel. 50 years. And you've completed 1/10,000th of the trip. Year 100. Everyone you knew is dead. The mission controllers who launched you have been dead for decades. Their children, now old themselves. Monitor your faint signals. You're a legend on Earth. The spacecraft that's been flying for a century, children learn about you in school. Scientists study your data. But to the people on Earth, you're ancient. A piece of living history. A ghost from their grandparents' time. You look out your window. Darkness. The stars don't look closer. They don't look farther. They just are. Eternal points of light that never change from your perspective. You're flying toward them at 60,000 kilometers per hour. And they don't get bigger, don't get brighter. It's like running toward a mountain that never gets closer. Year 500. Earth has changed beyond recognition. Languages have evolved. Countries have risen and fallen. Technology has advanced. The messages from Earth, if they still come, are incomprehensible. You're not just distant in space, you're distant in time. You're from a different era, a different age, a different civilization. You're alone in the darkness between stars, and you've never felt more forgotten. Year 1000. All of human civilization, from the first cities in Mesopotamia to the medieval period, fits inside your journey so far. The pyramids were built. Rome rose and fell. The Renaissance happened, and you've been flying the whole time. You're in the void now. Deep interstellar space. The sun is just another star among billions. You can't even tell which one is home anymore. They all look the same. Just points of light in the eternal darkness. Year 10,000. This is how long human civilization has existed. From the first permanent settlements to today, You've been flying that entire span of time, and you're still not even close to Proxima Centauri. Not even close. Year 40,000. Humans have changed, evolved. We're not the same species anymore. Our brains are different. Our bodies are different. Our societies are unrecognizable. You're from a different world, a different species, a different time. You're more alien to the humans of this era than any extraterrestrial could be. Year 80,000. Finally, after 80,000 years of flight, you see it. Proxima Centauri is getting brighter in your window. Not much. Still just a star, but definitely, measurably brighter, closer. You begin to slow down, except you can't. You have no fuel left to brake. You used it all at the beginning. Accelerating to this speed, so you fly past. You have a few hours, maybe a day, to take photos as you scream through the system at 60,000 kilometers per hour. Then you're gone, flying off into deeper space, into darkness beyond darkness. All that time, 80,000 years, and you get a few hours. But this is imagination. In reality, you can't fly for 80,000 years. A human body can't survive even 100 years. Your food would run out after months, maybe years if you rationed carefully. Your ship would break down. Systems would fail. You would die alone in the darkness between stars. Your body drifting forever in the void, never reaching anything. So let's imagine something different. Let's say we found a way to go faster. Much faster. Let's say we could travel at the speed of light. Destination 3, light speed. Still isn't enough. 2, 0, 0, 0 to 3, 0, 0, 0. Okay, let's imagine a miracle. Let's say we can travel at light speed, 300,000 kilometers per second, the maximum velocity the universe allows, the speed of causality itself. Nothing can go faster. Not because we don't know how, but because physics itself forbids it. But let's pretend we found a way. You climb aboard a ship that can travel at light speed. The moment you activate the engines, Earth vanishes behind you. Not gradually. Instantly, 1 second later, the moon is 400,000 kilometers away. You're already farther than any human has ever gone. And it's been 1 second. 3 minutes later, Mars is receding in your rearview mirror. Planets are blurs. Streaks in your window. You're moving so fast that the solar system feels tiny. 5 hours pass. You've cleared Pluto. Every planet is behind you. The sun is shrinking, the entire solar system. That vast expanse that takes our fastest probes years to cross. You've traversed it in half a day. 1 year later, you exit the Oort cloud. The solar system, that enormous sphere, 6,000 kilometers on our house scale, crossed in just 1 year. You're free. You're in interstellar space. Surely now, at this godlike speed, at the fastest speed the universe permits, surely you can reach other stars quickly. 4.3 years later, you reach Proxima Centauri. 4.3 years. Even at light speed, even at the absolute maximum velocity possible, even traveling as fast as the universe allows anything to travel. It still takes over 4 years to reach your nearest neighbor. You arrive, you orbit the star. It's smaller than our sun, dimmer, red instead of yellow. But it's a star. It has light, it has heat, and it has a planet. Proxima Centauri B. Rocky, roughly Earth-sized, maybe habitable, maybe not. You take your measurements. Then you look around. What else is near here? The next nearest star is about 4 light-years away. Then another cluster of stars within 10 light-years. Within 15 light-years, there are maybe 50 stars. Within 20, maybe 100. so you could visit them. At light speed, you could tour the nearest 100 stars in a human lifetime. Maybe 2 lifetimes. You'd grow old doing it. But it's possible. Except it's not, because you can't actually reach light speed, and even if you could, time dilation would make the journey strange. But let's ignore that for now. Let's keep imagining. You decide to go farther, to tour more of the galaxy, so you pick a destination. A star cluster, 500 light years away. Young stars. Maybe interesting planets. You fly for 500 years at light speed. When you arrive, you find beautiful things. Massive blue stars burning hot and bright, nebulae glowing in the light. Planets forming in disks of dust. It's stunning. You take your photos. You record your data. Then you look at the map of the Milky Way. You see where you are, and you realize something crushing. You've traveled 500 light years, 5 centuries at the fastest possible speed, and you've crossed 0.5% of the galaxy's diameter. The Milky Way is 100,000 light years across. 100,000. To cross it from edge to edge at light speed would take 100,000 years. Modern humans, Homo sapiens, have only existed for about 200,000 years. To cross our galaxy would take half the entire span of our species' existence. And you're already at light speed. You're already at maximum velocity. There's no faster to go. You look at the stars around you. 200 billion stars in the Milky Way. At light speed. Visiting just 1% of them would take millions of years. Tens of millions. To see them all, billions of years. The sun would die before you finished. Earth would be gone. The solar system would be dark and cold. But surely there's something closer. Some region worth exploring. The spiral arm you're in. Maybe just this local section of the galaxy. You map it out. The Orion Arm. Our section contains maybe 10 billion stars. 10 billion. At light speed, if you spent just 1 day at each star, just 24 hours to look around before moving on, it would take, let's see, 10 billion days. That's about 27 million years. 27 million years to do a 1-day flyby of each star in our local arm. And that's assuming you don't sleep. Don't stop. Don't take breaks. Just fly and observe. Fly and observe. For 27 million years straight. It's impossible. Not just difficult. Not just challenging. Fundamentally, physically, cosmically impossible. The Milky Way is too big. Even at light speed. Even at the fastest speed reality allows. It's too big to explore. Too big to travel, too big to know. And that's just our galaxy. You look beyond, through your ship's telescope. You see Andromeda, the nearest large galaxy. It's beautiful, a spiral like the Milky Way but bigger, brighter. It contains 1 trillion stars. How far? 2.5 million light years. At light speed, it would take 2.5 million years to reach Andromeda. 2.5 million. Longer than humans have existed. Longer than any species has survived unchanged. Longer than ice ages. Longer than continents take to drift. Longer than most mountains exist. 2.5 million years ago, our ancestors were Homo habilis. Barely human. Just learning to make stone tools. No language. No fire. No art. No music. No culture. Just survival. All of human evolution. From those first tool makers to the present day. All of that time would pass while you fly from the Milky Way to Andromeda. At light speed, and if you somehow made that journey, if you somehow survived 2.5 million years of flight, you'd arrive at another galaxy full of unreachable stars. Another 1 trillion destinations. Each one requiring years or centuries or millennia to visit. This is the real problem. You're already traveling at light speed. the universe's speed limit, the fastest anything can go according to the laws of physics. And it's not enough. It will never be enough. The universe is too big. The distances are too vast. Even at maximum velocity, even at the speed of causality itself. Space swallows you. Time swallows you. You're a tiny spark flying through an infinite darkness, and the darkness is too large to ever cross. Look at the numbers another way. The observable universe contains 2 trillion galaxies. 2 trillion, each one containing hundreds of billions of stars. If you wanted to visit just one star in each galaxy, just one single star per galaxy, at light speed, with no breaks, no stops, just instant teleportation from one galaxy to the next after touching one star, it would still take trillions of years. The universe itself is only 14 billion years old. You'd need to live 1,000 times longer than the universe has existed just to touch one star in each galaxy. And most of those galaxies are moving away from us. Space itself is expanding. Galaxies in distant parts of the universe are receding faster than light speed, not because they're moving through space that fast, but because space between us and them is growing. They're being carried away by the expansion of the universe itself. Those galaxies, unreachable, forever. Even at light speed, you could never catch up to them. You could fly for eternity, and they'd just get farther away. Imagine standing on a beach. The ocean stretches to the horizon. You can see islands in the distance, some close, some far. You want to swim to them, but as you watch, the islands start drifting away. Slowly at first, then faster. The close ones drift at a walking pace. The distant ones drift faster than you can run. The farthest ones disappear over the horizon, moving away faster than any boat could follow. That's the universe. It's not just big, it's getting bigger. The farther you look, the faster it's running away, even with light speed, even with the ultimate velocity. You're stuck, trapped in a region of space that keeps shrinking relative to the whole. The observable universe grows, but the reachable universe shrinks. You can see galaxies billions of light years away, but you can't reach them. Not with current technology, not with any foreseeable technology, not even with light speed. The universe itself is pulling them away faster than you can chase. So even in this fantasy, this imagination where we somehow achieve light speed, we're still trapped. Maybe we could visit a few thousand stars in our lifetime. Maybe explore a tiny bubble of the galaxy. But the vast majority of the universe, forever beyond reach. And remember, this is all fantasy. We can't actually travel at light speed. Why not? Destination 4. Why we can't fly. Fast 3000 to 4000. So why don't we just build a ship that travels at light speed, or even 10%, 20% of light speed? Why is it so hard? The answer comes down to 2 brutal realities: energy and Einstein. Let's start with energy. To make something go faster, you need fuel, chemical fuel, nuclear fuel, antimatter, whatever. You burn it, convert it to energy, and push yourself forward. Simple, in principle. But here's the problem. Fuel has mass. Fuel is heavy. And to move that fuel, you need more fuel, which is heavier, which needs even more fuel. Let me walk you through this with an example. Say you want to send a small probe to Proxima Centauri. The probe weighs 100 kilograms. That's light. About the weight of an adult human. Just instruments. A camera. A transmitter. No crew. No life support. Just the bare minimum. To accelerate this probe to 10% of light speed, which is 30,000 kilometers per second, you need to give it kinetic energy. The formula is 1/2 mass times velocity squared. Plug in the numbers. And you need about 45 trillion joules of energy. How much is that? Well, a kilogram of gasoline contains about 45 million joules of energy. So you'd need about 1 million kilograms of gasoline to accelerate your 100-kilogram probe. 1,000 tons of fuel for a 100-kilogram payload. Except it's worse than that, because now your ship doesn't weigh 100 kilograms. It weighs 1 million kilograms. Because of all that fuel, which means you need more energy to accelerate all that fuel, which means more fuel, which means more mass, which means more energy, which means more fuel. The rocket equation says that for every bit of payload, you need exponentially more fuel as you try to go faster. It's not linear, it's exponential. The amount of fuel grows insanely fast. To send that 100-kilogram probe to 10% of light speed using chemical rockets, you'd need a fuel tank thousands of times heavier than the probe. Millions of times heavier. The numbers become absurd. You'd need fuel equal to the mass of a mountain to send a probe the size of a person. Okay, so chemical rockets don't work. What about better fuel? What about nuclear fusion? Fusion is better. Much better. You get more energy per kilogram of fuel. Maybe 100 times more than chemical reactions. But the rocket equation still applies. You're still carrying mass. You still need exponential amounts of fuel. Engineers have done the math. To send even a tiny probe, a chip-sized probe, to 20% of light speed using the best fusion drives we can imagine, you'd need fuel weighing thousands of tons. To send something the size of a car, millions of tons. To send a ship big enough for humans, the fuel requirements become planetary. You'd need to convert an entire asteroid into fuel just to accelerate one ship. And that's just to accelerate. You also need fuel to slow down when you arrive. Otherwise, you'll fly right past your destination at tens of thousands of kilometers per second. So double all those numbers. What about antimatter? In science fiction, antimatter is the ultimate fuel. When matter meets antimatter, they annihilate completely, converting all their mass to pure energy. It's the most efficient possible reaction. E equals mc squared at 100% efficiency. Perfect. Right? Just use antimatter. Except we can't make antimatter. Well, we can. In particle accelerators, a few atoms at a time, it takes enormous amounts of energy to create even tiny amounts of antimatter. And then you have to store it, which is nearly impossible because it annihilates the moment it touches normal matter. All the antimatter ever created by humans, if you gathered it together, wouldn't be enough to power a light bulb for more than a few minutes. To fuel a starship would require, we don't even have estimates, millions of years of production with our current technology, billions. All the energy from all the stars in the galaxy, the numbers are so large they're meaningless. So fuel is problem one. The rocket equation crushes us. The amount of energy needed for fast interstellar travel is beyond anything we can imagine producing. But let's say we solved that. Let's say tomorrow someone invents a perfect engine, infinite energy, zero fuel mass, magical physics breaking technology. You still run into problem two. Einstein. Special relativity says that as you accelerate closer to light speed, your mass increases, not just a little, exponentially. The closer you get to light speed, the heavier you become from the perspective of the outside universe. At 50% of light speed, your mass is about 15% higher than normal. Okay, manageable. At 90% of light speed, your mass is more than double. You weigh twice as much as you did at rest. At 99% of light speed, your mass is 7 times normal. You need 7 times more energy to accelerate further. At 99.9%, your mass is 22 times normal. At 99.99%, 70 times normal. The closer you get to light speed, the heavier you become. and the more energy you need to go faster. It's asymptotic. You can never quite reach light speed because you'd need infinite energy to do so. This isn't a technology problem. This isn't we haven't figured it out yet. This is reality saying no. The universe has a speed limit, and it enforces it through the structure of space-time itself. So what's the fastest we can actually go right now? Our fastest probe, the Parker Solar Probe, reached 163 kilometers per second as it fell toward the sun, using the sun's gravity to accelerate. That's fast, incredibly fast by human standards. But it's 0.05% of light speed, not 5%, 0.05%. At that speed, reaching Proxima Centauri would take 25,000 years. There is a proposal called Breakthrough Starshot. The idea is clever. Instead of carrying fuel, you push the spacecraft from behind using powerful lasers on Earth. The spacecraft is tiny, just a few grams, with a huge reflective sail. The lasers hit the sail, pushing it, accelerating it without the spacecraft carrying any fuel at all. The goal is to reach 20% of light speed. 20%. If it works, the probe could reach Proxima in about 20 years. But it requires technology we don't have. Lasers powerful enough to push something across interstellar distances. Materials light enough and strong enough and reflective enough to survive. Sails that won't tear or melt. Perfect aim to hit a small target over trillions of kilometers. And even if we build it, even if it works, what do we get? A probe the size of a postage stamp flying past Proxima at 60,000 kilometers per second. It gets a few minutes to snap pictures as it screams through the system. Then it's gone, flying off into deep space forever. No slowing down, no orbiting, no exploring, just a high-speed flyby. And the pictures they'd transmit back to Earth at light speed. 4.5 years to arrive, so 20 years of flight, plus 4.5 years for the signal to return. 24 years after launch, we'd get a handful of blurry images of a planet 26 trillion kilometers away. That's our best realistic option. Not a journey, not exploration, just a distant photograph. What if we wanted to send humans? What if we wanted a ship that could slow down, orbit, explore, land, study, maybe even return? Then we'd need something completely different. We'd need a generation ship, a ship so large it's a floating city, with farms to grow food, recycling systems for air and water, radiation shielding, redundant systems, backups for backups. A ship that could support hundreds or thousands of people for decades or centuries. And who would volunteer to leave Earth forever, knowing they'll never see home again, knowing their children will live their entire lives on the ship, knowing only their descendants will reach the destination. Destination 5. The people who belong nowhere. 4000 to 5000. Imagine this. It's the year 2150. Humanity has decided to try. We've built a ship, a massive ship, a cylinder 500 meters long, rotating to create artificial gravity. Inside are gardens, apartments, workshops, schools. It's a floating city. 1,000 people have volunteered. Engineers, biologists, doctors, teachers, farmers, artists, young families with children, single adults looking for adventure, old couples wanting to contribute to humanity's greatest journey. All of them know the truth. They will never come back. They will die on this ship, or, if they're lucky, on whatever world they find. Earth will become a memory, then a story, then a myth. The destination is Proxima Centauri, 4.3 light-years away. The ship can accelerate to 5% of light speed, which is already an enormous achievement, requiring technology we don't yet have. At that speed, the journey will take 85 years. Launch day arrives. It's broadcast worldwide. Billions watch. The ship rises from Earth's orbit. Where it was assembled, massive engines ignite. Slowly, ponderously, the ship begins to move. Inside, the volunteers watch through windows as Earth shrinks. Blue and white, clouds swirling, continents visible, then smaller, a marble, then a dot, then just another point of light among many. Some people cry. Some are too excited to cry. Children press their faces to the glass, watching their home disappear. The journey has begun. Year 1. People settle into routines. There are jobs to do. The hydroponic gardens need tending. Systems need monitoring. Children need teaching. Life continues. Some people struggle with the confinement. Others adapt easily. A few break down, overwhelmed by what they've done. Psychologists help them cope. Babies are born. The first generation ship babies. They're special. They'll be the first humans who never knew Earth as more than a distant memory. Their parents tell them stories about rain, about oceans, about walking on ground that extends to the horizon. The babies don't understand yet. They will later. Year 5. The ship has reached its cruising speed, 5% of light speed. The engines shut down. From now on, they're coasting. No more thrust, just momentum carrying them across the void. It's quieter now. The rumble of engines has stopped. It feels strangely peaceful. People have adapted. The ship is home. There are gardens where vegetables grow under LED lights. There are common areas where people gather. There are schools where children learn. Life is different from Earth, but it's life. People fall in love. Cups form. More babies are born. But there's a strange tension. The older passengers, the ones who remember Earth, talk about it constantly. They tell stories about beaches, mountains, forests. They show pictures to their children. But the children are growing up here, on this ship. To them, Earth is just a story. They've never felt rain, never seen a real tree, never stood under an open sky. The generation gap is starting. Year 10, the first death, an older passenger, one who was in his 60s when they launched, passes away from a heart attack. The crew holds a ceremony. They open the airlock. His body, wrapped in cloth, is released into space. It drifts away, tumbling slowly, and disappears into the darkness. It's sobering. Everyone knew this would happen eventually, but seeing it makes it real. People will die on this journey. Many people, most of the original passengers, won't survive to see Proxima. More babies are born. The population stays roughly stable. When someone dies, someone new is born. The ship isn't growing, just changing. The first generation is aging. The second generation is entering adulthood. The third generation is being born. Year 20. Earth sends a message. It took 4 years to arrive because the ship is now so far away. The message contains news, political changes, scientific discoveries, cultural trends. The passengers watch, listening to voices from home. But it feels strange. The news is about people they don't know, events they don't care about. The cultural references are confusing. Earth is changing, and so is the ship. They're growing apart. Someone calculates that by the time they reach Proxima, Earth will be almost 90 years ahead in its timeline. Nearly a century of changes. New technology, new politics, new generations. The Earth they left will be ancient history. They're not traveling in space. They're traveling in time, moving into a future where Earth has moved on without them. Year 30. The second generation is having children. These are the third-generation passengers, born on the ship. Parents, born on the ship. Only grandparents remember Earth. These children grow up hearing stories about Earth like fairy tales. Once upon a time, there was a world with blue skies and green grass. It sounds magical, unreal. How can sky be blue? Sky is metal. Everyone knows that. The teachers try to explain. They show pictures, videos. But to these children, it's like showing pictures of fantasy worlds. Beautiful, but not real. Not their reality. Some of the second generation are starting to question the mission. Why are we doing this, they ask. We didn't choose this. Our parents chose for us. We've spent our entire lives on this ship. For what? To reach a planet we've never seen. There are arguments. Some want to turn back. The ship debates. In the end, they vote to continue. The mission is bigger than any individual. Humanity's future might depend on this, but the resentment remains. Year 40. The first generation is almost gone. Only a few elderly survivors remain. They sit in the common areas, telling stories about Earth to anyone who'll listen. About cities with millions of people. About traveling hundreds of kilometers in a day. About weather, seasons, wildlife. The younger generations listen politely, but it's clear they don't really understand. How can they? They've never experienced it. Earth is an abstraction, a legend, not home. Year 50. Halfway point. The ship holds a ceremony. 50 years down, 35 to go. People celebrate, but it's bittersweet. None of the original passengers are left. Everyone on the ship now was either born here or boarded as a young child. The fourth generation is growing up. These are children whose grandparents were born on the ship. To them, this is all there is. The ship is the universe. They know intellectually that there's more, that there's a destination, but emotionally, this is life. This is everything. Year 60. A message arrives from Earth. It was sent 10 years ago. It says, "We've developed new propulsion technology. We could build a faster ship now. It would reach Proxima in 30 years instead of 85. The crew reads this in stunned silence. The math is obvious. If Earth builds that ship now, it will arrive at Proxima 15 years before this ship does. They've been traveling for 60 years, and they're about to be obsolete. What should they do? Turn back, continue? They debate for months. Emotions run high. Some are angry. Some are devastated. Some are relieved. Finally, they vote. The decision is to continue. We started this journey. We'll finish it. But morale takes a hit. They're no longer pioneers. They're the slow ship. The backup plan, the outdated mission. It's hard to stay motivated. Year 70. Life continues. The fourth generation is having children. The fifth generation is being born. These children have parents, grandparents, and even great-grandparents who never knew Earth. The chain of memory has broken. Earth is prehistory, ancient, mythical. The ship receives occasional messages from Earth, but they're harder to understand. Language has drifted. Slang has changed. Cultural references are incomprehensible. The gap is too wide now. They're from different worlds. Year 85. Proxima Centauri looms large in the windows. After 85 years, they're finally arriving. The engines fire for the first time in 8 decades, beginning the deceleration burn. The ship shakes. People who've never felt thrust before are thrown to the ground. It's violent, alarming, but necessary. Over months, they slow down. Proxima gets brighter. They orbit the star. Below is Proxima B. Rocky, reddish-brown, under the dim light of the red dwarf star. Instruments detect an atmosphere, water vapor, maybe oceans, maybe life. They send a signal to Earth. We've arrived. Proxima Bay is here. We made it. The signal travels for 4 years. Then, 4 years later, a reply comes back. Congratulations. The second ship arrived 15 years ago. They've established a colony on the surface. Population is now 5,000. They're doing well. Welcome to Proxima. The Generation ship crew reads this in silence. They're not the first, not pioneers. They're the second ship, the slower ship, the one that took too long. Below them, on Proxima B, there's already a thriving colony. People born on that planet. Kids who know Proxima as home. A second generation of colonists. And who are the Generation ship people? They're not from Earth. They've never been there. They were born in space. But they're not from Proxima either. They just arrived. They're visitors. Newcomers to a world that's already settled. They belong nowhere. Not Earth. Not Proxima. Not even the ship, which will be decommissioned now that the journey is over. They're people caught between worlds, between times, temporal refugees from a journey that took too long. This is the cost, not just the years, not just the distance, but the loss of belonging, the loss of home, the loss of connection to anything stable or permanent. And this assumes everything goes right. No major breakdowns. No catastrophic failures, no rebellions or psychological collapses, just a smooth, successful journey. In reality, it would be messier, harder, more tragic. Destination 6. An island in the dark ocean. 5000 to 6000. So here we are. Here's the truth we've been circling. We're trapped. Not trapped on Earth, though that's part of it. Trapped in the solar system, trapped by physics, trapped by distance and time and the fundamental structure of reality. Let me show you what I mean. Let's pull back. Not physically. You can't actually do this, but in imagination, in our mind's eye. Let's zoom out and see where we really are in the cosmos. Start here. You're standing on Earth. You can see about 5 kilometers to the horizon before the curve of the planet hides everything beyond. That's your world at ground level. That's human scale. Zoom out. Earth becomes visible as a sphere. Blue oceans covering 70% of the surface. White clouds swirling. Brown continents. Green where forests grow. It's beautiful. Alive. The moon orbits nearby. Grey and dead, but familiar. This is home. The only place humans have actually walked and lived. Keep zooming. The solar system appears. The sun at the center. A yellow star of medium size. 8 planets in their orbits. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune. They look close together in this view, like beads on a string. But remember the actual distances. Months of travel between them. Years to reach the outer planets. This isn't a cozy neighborhood. It's a vast expanse where worlds are separated by gulfs that take lifetimes to cross with our current technology. Still, this is our yard, our neighborhood, the space we could theoretically reach and explore. Even if it takes decades, keep pulling back. The solar system shrinks. Now you can see the nearest stars, dozens of them. Proxima Centauri, the closest, is visible as a separate point. Alpha Centauri A and B, a binary pair. Barnard Star, Wolf 359, Sirius, the brightest star in our night sky. They're scattered through this volume of space like islands in an ocean, each one light years from the others. Proxima, the nearest, is 4 light years away. The others are further. 6 light years, 8, 10, 12. This is our local neighborhood. Maybe 50 stars within 15 light years. Some have planets. Most probably do. A few of those planets might be habitable. This is the region we could maybe, possibly, theoretically reach if we had the technology. If we built generation ships, if we committed centuries to the journey, further out, hundreds of stars now, thousands. This is our spiral arm, the Orion arm of the Milky Way. The stars here form a loose structure, a river of suns flowing through space. But even in this crowd, the distances are enormous. Most stars are separated by years of light-speed travel, decades, centuries. You can see the structure now. Stars aren't randomly scattered. They cluster along the spiral arm, with darker regions between. But each star is still isolated, still alone in its own bubble of space. Zoom out more. The whole galaxy comes into view. The Milky Way, a barred spiral galaxy, 100,000 light-years across, 200 billion stars, arranged in a disk with spiral arms curling outward from the center. It's stunning, majestic, one of the most beautiful structures in the universe. But think about what you're seeing. Each point of light is a sun. Many have planets. Some of those planets might have life. And the vast, overwhelming majority are completely unreachable, even at light speed, which we can't achieve. You couldn't explore this galaxy in a human lifetime. You couldn't visit even 1% of it. Not in 100 lifetimes. Not in 1,000. Most of these stars will never be visited by anyone from Earth. They'll burn for billions of years, live out their entire lives, explode or fade. And we'll never know what worlds orbited them, what life might have evolved there, what wonders existed. They're forever beyond our reach. Still further out, the Milky Way shrinks. Other galaxies appear. Andromeda, the nearest large spiral, twice the size of the Milky Way and heading toward us. Though it won't collide for another 4 billion years. The Magellanic Clouds, smaller, irregular galaxies orbiting the Milky Way like satellites, dozens of dwarf galaxies scattered around us. This is the local group, about 50 galaxies bound together by gravity. They range in size from massive spirals to tiny dwarfs containing only a few billion stars. Together they form a loose cluster spanning several million light-years. Millions. Even light takes millions of years to cross these distances. All of human history, all of civilization, could fit into the time it takes light to travel from one galaxy to another in this group. Zoom out again. The local group becomes a point. Now you see the Virgo supercluster, thousands of galaxies arranged in a massive web, filaments of galaxies stretching across space, clusters and groups connected by thin streams of matter, voids between them. Enormous empty regions where few galaxies exist. The structure looks organic, like neurons in a brain, like the circulatory system, like fungal networks under a forest. The universe has structure at every scale, and at this scale, galaxies are the basic units. Further still, the Virgo supercluster is revealed to be part of something even larger, the Laniakea supercluster. 100,000 galaxies, a structure 500 million light-years across. Our home at the largest scale we can meaningfully define, and beyond Laniakea, more superclusters, hundreds of them, thousands, all connected in the cosmic web, the largest structure in the universe. Filaments of galaxies stretching across billions of light-years, vast voids between them where almost nothing exists. It's the skeleton of the cosmos. The framework of everything. This is the observable universe. Everything we can see, 93 billion light-years across. 2 trillion galaxies. Each galaxy containing hundreds of billions of stars. Each star potentially hosting planets. The numbers are so vast, they lose meaning. And now, let's zoom back in. Past the cosmic web, past the superclusters, past the Virgo supercluster, past the local group. past Andromeda, back to the Milky Way, back to the Orion Arm, back to our stellar neighborhood, back to the solar system. Here, right here, 8 planets, 1 star, and of those 8 planets, we've only ever walked on 1. Everything you just saw, all those stars and galaxies and superclusters, we can see them through telescopes, through instruments. We can photograph them, study them, measure them. We know they're there. We know their distances, their compositions, their motions. But we can't reach them, not in any meaningful way. Not with current technology. Not with any foreseeable technology. Possibly not ever. The observable universe contains 2 trillion galaxies. 2 trillion, each with hundreds of billions of stars. If even a tiny fraction of those stars have planets, and a tiny fraction of those planets have life, there could be trillions of living worlds out there. Trillions. And we can't reach any of them. We're separated by distances so vast that even light, the fastest thing in existence, takes millions or billions of years to cross the gaps. We're isolated, quarantined, trapped in our tiny corner of space by the sheer scale of the cosmos. How much of the universe could we realistically reach? Let's be wildly optimistic. Let's say we develop incredible technology, fusion drives, generation ships. Maybe we achieve 10% of light speed. And let's say we spread out over thousands of years, colonizing every star we can reach. How far could we get? Maybe a few hundred light years. 1,000 if we're really ambitious and patient. That's a sphere around Earth containing maybe a few million stars. A few million out of 200 billion in our galaxy. That's 0.001%, 1,000th of 1% of the Milky Way. And the other galaxies, the trillions of other galaxies in the observable universe, completely, utterly, forever unreachable. We could send light-speed messages to them. Signals would arrive millions or billions of years in the future, long after our civilization is gone, long after humans have evolved into something else or gone extinct, long after the sun has died. But visit them, never, not unless the laws of physics are completely wrong, which they probably aren't. It's like living in a house with enormous windows, floor-to-ceiling glass, looking out on an infinite city. You can see millions of buildings, millions of lights, activity everywhere, life happening on every street, in every structure, across every horizon. But you can't leave your room. The door is locked, not by any person, not by malice, not by some keeper or jailer, but by the fundamental architecture of reality. Space is too big, time is too short, speed has a limit. The door is locked because that's how the universe is built. You're not in a cell. You're not in a prison. Exactly. You have space. Your room is large. You can move around, explore a little. You have windows with amazing views. You're not suffering, but you're still trapped. Compared to what you can see, compared to the vast city visible through the windows, you're confined to the tiniest fraction of space. We are islands of light in an ocean of darkness, and the ocean is too wide, too deep, too vast to ever cross. That's where we are. That's what we are. An island floating in the cosmic dark. Destination 7. The gift of limitation. 6000 to 7500. And here's the strange thing. Here's the twist that changes everything. Not being able to travel far might be the greatest gift the universe ever gave us. Think about it for a moment. Really think about it. If we could travel anywhere, would here matter? If we could reach every star, would home be special? If the entire galaxy was accessible, would this planet, this solar system, this precise place where you are right now have any meaning? When everything is reachable, nothing is precious, but we can't go anywhere. We're bound here, and because we're bound, Everything that matters has to happen here. Every human who ever lived, every person who laughed or cried, every story ever told around a fire, every song ever sung, every work of art ever created, every scientific discovery, every moment of love, of heartbreak, of triumph, of loss, every kiss, every birth, every death, every dream, every fear, every hope, all of it, every single moment of human experience across all of history, it all happened right here, in this tiny bubble, on this pale blue dot, orbiting an ordinary star in an unremarkable galaxy, your ancestors, going back 10,000 generations, all lived and died on Earth. Every person you've ever met was born on Earth. Every conversation you've ever had took place within a few thousand kilometers of where you were born. Every beautiful sunset you've watched, every meal you've enjoyed, every person you've loved, every place you've felt at home, all of it within this impossibly tiny region of space. And that's not because we lacked imagination. We dreamed, we looked up at the stars and wondered what was out there. We built telescopes to see farther. We sent probes to explore our solar system. We walked on the moon. We tried to reach beyond. But the universe said no, gently but firmly. No, this is your place. It said, make it matter. And we have. We have made it matter. Everything meaningful in human experience happened right here because it had to. There was nowhere else to go. Think about Voyager 1 again. That little spacecraft we launched in 1977. It's been flying for 49 years, farther than anything else we've made. And in 1990, when it was at the edge of the solar system, scientists did something beautiful. They turned its camera around, pointed it back toward home, and took a picture. In that image, Earth appears as a single pixel, less than 1 pixel. A pale blue dot suspended in a sunbeam. If you didn't know what you were looking for, you'd miss it entirely. It's that small. Carl Sagan saw that image and wrote something that still gives me chills. He said, look at that dot. That's here. That's home. That's us. Everyone you love. Everyone you know. Everyone you ever heard of. Every human being who ever was lived out their lives on that dot. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, every hopeful child, inventor and explorer, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. All of that, everything, on that dot, and we can't leave it, not really. We can't go to other dots. We're bound to this one, maybe forever. But that's not a curse. That's the thing that makes it sacred. It means this dot matters. It means everything that happens here is everything. There's no backup world, no second Earth waiting somewhere else, no escape hatch. This is it. This is all we have, and that makes it infinitely precious. Think about your own life, the people you love, your family, your friends, the places you've been, the moments that shaped you, the experiences that made you who you are. All of it happened within a tiny range. You've probably never traveled more than 20,000 kilometers from where you were born. Most people haven't. That's halfway around Earth. Nothing on the cosmic scale. And yet, within that tiny range, you've experienced everything that matters. You've felt wonder looking at the stars. You've felt love holding someone's hand. You've tasted food that made you happy. You've heard music that moved you. You've seen beauty that took your breath away. You've been sad. You've been joyful. You've been angry and calm and confused and clear. You've learned things. You've grown. You've changed. You didn't need to travel light years to feel complete. You didn't need to visit other stars to live a meaningful life. Everything you needed was here, within reach. Within this small bubble we call home. That's the gift. The limitation isn't a prison, it's a focusing lens. It concentrates existence. It makes here matter. It makes now matter. It makes this planet, this moment, this life, irreplaceable. If we could go anywhere, we'd always be looking outward, always wondering if somewhere else was better, always restless, always searching, never satisfied, never home, but we can't go anywhere. So we have to be here. And being forced to be here, we've made here beautiful. We've created art, music, literature, science, philosophy. We've built cities and cultures. We've developed technology. We've learned to cooperate, to love, to care for each other. We've created meaning from meaninglessness. Not because we're special, not because we're chosen, but because we're here. And here is all we have. Imagine a future, maybe 1,000 years from now, maybe 10,000. Humans have spread beyond Earth. We've colonized Mars. We've built habitats in the asteroid belt. Maybe we've sent generation ships to nearby stars. A few million people living on other worlds. But Earth still holds billions of people. It's still the center of human civilization. Not because it's the biggest or richest or most advanced world, but because it's home, because every story we tell starts here. Every myth, every legend, every religious text, every historical event, every ancestor we honor, they're all from Earth. The children born on Mars will look up at the night sky and see a blue star, a little brighter than the others. And they'll know, that's Earth. That's where we came from. And maybe they'll feel what you feel when you look at old photographs. Nostalgia, longing, a sense that no matter where you go, part of you is still there. The generation ship children, the ones born in transit to distant stars. They'll look back at the sun growing dimmer behind them, just another yellow star among billions. And they'll know their ancestors came from there. From that system, from that pale blue dot. We're not trapped in a prison. We're rooted in a home. And roots aren't chains. Roots are what let you grow. They anchor you. They give you stability. They provide nourishment. Without roots, you drift. You blow away in the wind. You have no foundation. Our limitation, our inability to go anywhere, is our root system. It keeps us grounded. Literally, it forces us to invest in here, to care for this world, to build something lasting. If we could leave whenever things got hard, we would. If we could abandon Earth for another planet when we damage this one, we might, but we can't. So we have to fix things. We have to make this work. The limitation is teaching us responsibility, teaching us to value what we have, teaching us that this fragile blue world floating in the void is all we get. So we'd better take care of it. That's the gift. Not freedom, not unlimited possibility, but constraint that creates meaning. A blank canvas is paralyzing. Infinite options are overwhelming. But give an artist one canvas, one set of paints, and say this is all you have, and they create masterpieces. Give humanity one planet and say this is all you have, and we create civilization. Closing meditation 7500 to 8000. Tonight, as you rest, as your breathing slows and sleep begins to pull you under, think about this. You're lying here in this moment on a planet spinning through space. That planet is rotating, carrying you at 1,500 kilometers per hour. You don't feel it. Everything feels still. The bed beneath you feels solid and unmoving. But you're spinning, right now, as you listen to these words, and that spinning planet is also orbiting the sun. racing through space at 100,000 kilometers per hour, 30 kilometers every second, faster than any bullet, any rocket, any spacecraft we've ever built. You don't feel that either. You feel peaceful, calm, at rest, and the sun itself is orbiting the center of the galaxy, carrying you, carrying Earth, carrying everything at 800,000 kilometers per hour. The entire solar system is moving through space in a vast cosmic dance that's been happening for 4.5 billion years. You're moving, always moving, through space at speeds that would terrify you if you could feel them. But you can't. You feel still. You feel safe. And you are safe. Because even though you're moving through space, you're not going anywhere. You're staying here, in this solar system, on this planet, in this place that physics has made your home. The stars outside are unreachable. You know that now. They'll always be distant, always beautiful, always beckoning, always impossible. And that's okay, because everything you need is here. Everyone you can love is here. Every moment of beauty you'll ever experience. Every challenge you'll face. Every discovery you'll make. It's all here. Voyager 1 is still flying. Right now. As you drift towards sleep, it's out there in the darkness, still sending back faint signals, still carrying that golden record with sounds of Earth, waves and birds and human voices saying hello to the cosmos. 49 years of flight, and it's still in our neighborhood, still part of our family. Maybe someday, thousands of years from now, another civilization will find it. They'll decipher the golden record. They'll hear our music, our voices, and they'll wonder about us, where we came from, where we went. And maybe they'll understand. Maybe they face the same limits. Maybe they're also trapped by distance and time. Maybe they're also islands in the darkness, looking up at stars they can never reach. Maybe the universe is full of civilizations like ours. All of us isolated, all of us looking outward and dreaming, all of us bound to our homes by the sheer scale of space. Maybe everyone is trapped. Maybe that's just how it is. And maybe that's beautiful. Maybe that's how it should be, because if we could all travel everywhere, if space was small and easy to cross, would it still feel magical? Would the stars still inspire wonder? Would we still feel this deep, humbling awe when we look up at the night sky? Or would it all become mundane, just another place to visit, just another destination checked off a list? Maybe the distance is what makes it beautiful. Maybe the impossibility is what makes it meaningful. You're lying here now, safe, warm, bound to this place, and somewhere out there, across billions of light years, other beings might be doing the same thing, lying under their own skies, looking at their own stars, feeling small, feeling trapped, feeling precious. All of us together, separated by impossible distances, but united by the same wonder, the same curiosity, the same longing. We're not alone in being alone. And somehow, that's comforting. Sleep now. Let the universe spin around you. Let the cosmos do its ancient dance. You're part of it. A small part. Yes, a tiny part, but a part nonetheless. You belong here, in this moment, on this world, under these stars that you'll never reach. And that's not sad. That's not tragic. That's home. Every person you love is within reach. Every place you can go is accessible. Every experience you'll have is possible right here. You don't need the stars. You have something better. You have here. You have now. You have this. The universe is vast, unimaginably vast. But you're not meant to contain it all. You're meant to be contained by it, held by it, kept safe in this tiny bubble of warmth and light. Rest now. Close your eyes. Let your breathing slow. The stars will still be there tomorrow. Still distant. Still beautiful. Still unreachable. and you'll still be here, still wondering, still dreaming, still alive, on this pale blue dot, this island in the darkness, this home, welcome home. You've always been home. You'll always be home, and that's enough. That's more than enough. That's everything. Sleep well.